Backcountry skiing, snowboarding, snowmobiling, and snowshoeing have all been prominent and enjoyed activities for years on end. Every person who enters the backcountry, whether it be through open gates at a resort or highway pull-offs in the mountains, is in immediate danger of avalanches. An average of 25 people in the U.S. die yearly in avalanche incidents, and the number of non-fatal accidents is far, far higher. With a constantly increasing number of backcountry users, this statistic is on the rise. This issue is incredibly important to society because an increasing number of people are at risk yearly, an increasing number of people die yearly. We need to do something to protect backcountry users. The first step to prevention is understanding. For a life-threatening avalanche to occur, three main factors must align. First, the slope must be on a slope angle that can produce a slide. Second, there must be an unstable snowpack. This could mean a buried weak layer or just a bunch of new snow. Third, there must be some type of stressor. While what first comes to mind may be a skier or snowboarder on the slope, it unfortunately isn't quite as simple as this. This snow, rain, or even warming temperatures can all be considered stressors that cause avalanches. This is incredibly important to understand because it means that hikers in flat zones or gullies aren't necessarily out of the woods. Slopes around them can slide naturally, leaving them buried and helpless. First off, slope angles. This is an incredibly important variable to assess when in the backcountry. Very often people are told of the magical 38 degrees. This number, statistically, is where the majority of avalanches occur. The fault with using this number, however, is that all avalanche statistics are greatly dominated and skewed by Colorado depth hoar incidents. The biggest problem causer in our mountains, and the slide I will be talking about today, is a persistent weak layer. For these, the prime sliding angle is between 35 and 40 degrees. Now for our second angle, snowpack. The snowpack we will talk about, a persistent weak layer snowpack, consists of three main parts. First off, the majority have a sliding layer, closest to the ground. This sliding layer is often an ice crust or packed settled snow. On top of that, we have our weak layer. The weak layer is a layer of snow grain. The layer of snow grain that doesn't mesh well with what is above or below it. Essentially, we would have bigger, more fragile crystals that don't mesh together in our snowpack. On top of that, we have a slab. A slab can be any new or consolidated snow. The snow could be transported by wind or by a storm, but once it settles and compacts into itself on top of a weak layer like facets, an avalanche is imminent. When weight is applied to the top of this snowpack, the weak layer collapses. With this collapse, the slab loses its surface tension and slides down the hill in a deadly and destructive avalanche. Facets are a deadly snow grain that we run into fairly often in the mountains around Boise and McCall. They are more often than not the culprit in avalanches near us. Their formation is where we really get into the science. It's truly fascinating. Facets form in a sublimation and deposition event that relays water vapor throughout the snowpack. This can only happen with relatively large temperature gradients in the snowpack. Let's say, for instance, we have a snowpack, and between 50 centimeters and 60 centimeters below the surface, we have a temperature change amounting to 1.2 degrees Celsius. What happens is the warmer side of that 10 centimeters has drastically more energy than the cooler side. The side with more energy, let's say the bottom 5 centimeters, will begin to sublimate and turn into water vapor. This goes through the temperature. This water vapor then rises towards the top of the snowpack, and as it goes through the temperature gradient, its surroundings now have drastically lower energy. The water vapor begins to deposit on these snow grains in this upper 5 centimeters of crystal. This deposition gradually adds body to particles and makes them drastically larger. While the snow crystals do get large, they also become angular and do not mesh well with each other at all. To give you a better visual of facets, they are often described as large, sugary snow. This snow layer is an incredibly weak layer of snow in our snowpack, one that consistently causes problems. I performed a demonstration with the goal of proving the difference in avalanche danger for a snowpack with facets and one without. They were both set up on the same sliding surface, and their slope angles were increased together to lower the chance of error. The result perfectly demonstrates the danger of faceted layers in our snowpack. With Scotch packing tape on both sides. This allowed me to keep the sliding surface. First, I layered a piece of plastic with Scotch packaging tape on both sides. This allowed me to keep the sliding surface a control variable. I separated it with masking tape. I then used a BCA inclinometer on the side so I can watch the slope. Now we need two 87-gram samples of powdered sugar. This will represent fresh snow, what we want to be skiing. Next, we get 26 grams of regular sugar. This will represent facets. Now we'll layer powdered sugar on the side with the inclinometer. This represents fresh, good snow on top of an ice crust with no weak layers beneath it. We'll spread it around to keep it uniform throughout. On the other side, however, we'll first layer granulated sugar on top of the ice crust. This represents facets on top of an ice crust. Now we'll come with our 87 grams of powdered sugar and layer it all over. Again, we'll move it around to keep it uniform throughout and do the little packing thing to keep the two sides the same. What we have represented now is fresh snow on top of an ice crust and fresh snow with facets beneath it on top of the ice crust. Now let's see how this plays out as we steepen the slope angle of both sides. Remember, faceted layer on the left, regular snow layer on the right with the inclinometer. Boom, there goes the faceted layer, right between 35 and 40, which is what we talked about earlier. Now just for kicks, let's see when there it goes. Right between 50 and 55. Overall, this experiment confirmed two things. The first being that facets on top of an ice crust underneath the snow layer cause big problems in the snowpack. The second thing that this experiment illustrated has more to do with slope angle than anything else. This showed perfectly that 35 to 40 degree range is where problems really occur.